Hey friends, welcome to follow up. And in this video, we're going to have a look at problem 204, count primes. So this video is a warm-up for problem 2601, prime subtraction operation. So in this problem, we are given an integer n. We would like to return the number of prime numbers that are strictly less than n, right? So here, if you look at the three examples, example 2 and example 3 are very special because n equals 0 and 1. So there are no primes less than 2. So here we mean non-negative ones. So here, if we look at 10, so we can count the primes. There are 2, 3, 5, 7. So there are 4 primes. So the constraints for this problem, or we can regard this as an additional assumption, is that n can be as large as 5 times 10 to the power 6. So this number is a decent large number. In other words, when we solve this problem, we need to think of the time complexity of the algorithm. So in this video, we're going to solve this problem using the Sieve of Eratosthenes. So here you can see this Wikipedia page. So here the method or the algorithm will be the sieve, right? So here Eratosthenes. So you can actually so this man, if I remember correctly, it's a Greek mathematician and philosopher. It's 276 BC to 194 BC. Yeah. So if this algorithm actually is not that complicated, so this is the details for the algorithm. So basically, it says that if you identified a prime, then all its multiples cannot be a prime, right? So here the procedure for this algorithm is the following. So we create a list consecutive integers from 2 through n, right? Then initially let p equals 2 and the smallest prime number, right? Then we enumerate the multiples of p by counting in increment of p from 2p to n and mark them in the list as they marked, so they are not primes. So next, so basically find the smallest number in the list greater than p that is not marked. Yeah, if there was no such number, then this we can stop here. Otherwise, let p now equals this new number and then repeat step 3. So when the algorithm terminates, the numbers remaining not marked in the list are all the primes below n. So here is a refinement. As a refinement, it's sufficient to mark the numbers in step 3 starting from p squared. The reason is that as all the smaller multiples of p will have already been marked at that point, right? So basically, this is the algorithm of the Eratosthenes. So basically, you can review this for examples. For example, if we want to find the primes less than or equal to 30, you list them from 2 to 30. Then you first mark the multiples of 2, right? So this marked with a crossing line will not be primes. Then we marked multiples of 3. So we can mark 6, but it's already marked. So actually we can start from 3 squared, that is 9. So we mark this, and then 15, right? And so on. So after that, so you can mark the multiples of 5. We can start from 25, right? So we mark this one. So we're going to up to here. Now here is 7. So we can start from 7 squared, that is 49. But 49 is out of bounds, so we can stop here. So this left unmarked will be the primes below 30. So this is the algorithm. Here is the pseudocode, right? So actually, we just need to translate this code into Python code for solving this problem. So here the time complexity is O log n, right? So actually, for the analysis of the term complexity, it needs some mathematical background. If you have background in mathematics, so it will be very straightforward. So with that said, let's come back to the coding part. So here, in order to accelerate a little bit, here I can choose to use NumPy. So import NumPy as NP. See, so this is a very typical import for data analytics. If you are familiar with NumPy or another related library like pandas and so on, but it's not necessary to use. This NumPy library in this problem. You can use plain Python. It still do the job, but slightly slower. The coding format is almost identical. So let's choose to use this one. So here, once we have this one, first let me emphasize. Here we want to return the number of primes that are strictly less than n, right? So here, let's see if n is less than or equal to 2. In this problem, n is non-negative, right? So we just need to return 0, because there are no non-negative primes below 2. And next, basically, we want to use some flags or marks as in the Wikipedia page. So let's use flags. So we're going to so first initialize a array of length n, right? So basically, they are all true, right? And then so this will be, the index will correspond to the number, because this length is n, so the index will from 0 to 1 up to n minus 1, right? We want to select the numbers, prime numbers among these n numbers. These n are from 0 up to n minus 1, right? Because it's strictly less than n. So first I'm going to mark flags and 0 and flags 1 to be false, right? Because they are not prime numbers. And then we can use the sieve, right? So for this, we just need to iterate for I in range. So we can start from 2, the smallest prime number, and then we can up to this. We can say n to the power 0.5, basically square root, right? Then plus 1, right? So because this will end at this integer, right? Because this index is not included. And then we are going to use the identical algorithm. So we check if flags I is prime, then we're going to check its multiples. So we're going to start from I square, right? Then the step will be I, right? And then we want to set all this to be false. So here actually we used a format of broadcasting. So that's about it. Next, we just need to sum the entries, right? Or if you use true or false here, you can use 1 or 0, right? But we can directly do the sums. So we just need to return np sum of flags. So this will be the number of prime numbers. So before we make any comments, let's first do a test. Yeah, it passes the first example. It will pass the second and third example because this is treated as a special case. Now let's look at the generic case. Yeah, it passed all the cases fast enough. So here, let me see. Let's print out the flag also. Print. Let's see. Let's do this. Let's print this dictionary. I and flag for I flag in enumerate flags. So let's test for 10, right? Yeah, basically it tells which number is prime, right? So 2 is prime, 3 is prime, and 7 is prime. And that's it, right? 2, 3, 5, 7. That's 4. So with that said, basically that's about it for this video. So here I choose to use NumPy. This is just for the convenience of computation. So you can use plain Python, right? So with that said, that's it. So we are going to explain another problem, that is problem 2601, using this one as a basics. With that said, that's it.